Since last Friday, we do a review for the test and the test, so we did not have time to go over the lesson. And the lessons that we're gonna start in, supposed to start on Friday, is the Unit 3, Lesson 1. And Unit 3 is gonna be uh, derivative application of derivative. So we're gonna look into the application. And the first lesson is extrema of a function. So definitions of extrema. So let f be defined on an interval I containing c. C is the point that have x equals c. So the f of c is a minimum uh, if f of c less than f of x for all x in I. What does that mean? It means that fc is the lowest level of the function in that interval I. Okay. F of c is a maximum of f on interval I is greater or equal f of x. Same, max had to be, f of c had to be greater than owner f of x. All right, the minimum and maximum of function of an interval are called extreme value, or short for extrema of the function. Okay, and the minimum and maximum function are also called absolute max or mean. We also call global max or mean. We're gonna using absolute max and mean since the AP calculus college board use it. It's rarely using as a global max and mean. Okay, so we stick with absolute max and absolute mean. Okay, so there is a theorem. It's called extreme value theorem, and that's called EVT. So remember the name EVT, and EVT gonna be extreme value theorem. It required the function f had to be continuous in the closed interval a and b. Then it will guarantee that you have both a minimum and a maximum in that interval. So require that continuous on the closed interval a and b. Okay, so that means that if you have a hole or infinity, it does not qualify for maximum minimum. So the theorem, it doesn't apply for the whole infinity. And we're going to go over to the example so you can see clearly. So let's look at example 1. Okay, example 1, the function is continuous on a closed interval, a and b. And I want to making the b lower. Okay, so in that case, the theorem, the EVT guarantee that we have a max. Okay, that's a maximum that we're having here. That's an absolute max. And we have also absolute mean. I mean, I put it max in here, but in the extreme theorem, we're talking about the absolute max and mean on that closed interval. So mean and max here, mean, absolute max. Okay, A is not a mean or max. Let's look at the second example. In this case, second example, they have a hole. So it is not continuous on the closed interval. All right, so we have only the absolute mean at x equal a, but at b we don't have a max in there. And remember, when they have a hole, you don't know the max. Max and mean had to having a concrete number associated with that. But the hole, we don't know exactly where it is. Even though that we learned already limit when x approach b equal f of b, if f of b exists, or in this case here, we don't know if f of b exists or not, but we know that going to be closing to f of b in here. Okay. So look at the third example. The third example is fail the theorem is because it's not on a closed interval. And you see the two arrow, which mean that the function um, is defined in domain from negative infinity to positive infinity. And the arrow on the right side mean the function gonna go to infinity, and the left side the function going to negative infinity. So therefore, infinity do not qualify for max and mean. Doesn't guarantee the EVT doesn't guarantee maximum or minimum for any function that has infinity. So had to be on closed interval. So in order to be able to guarantee to have a absolute max and an absolute mean in this case, you have to restrict. Okay, instead of arrow, we're gonna stopping somewhere in here like a B and like a A. So the two arrow had to be replaced by a solid point. So we have absolute extrema, which is absolute mean, absolute absolute mean, absolute max. And then we have relative extrema, and relative extrema also called local extrema. And I want to using local extrema because it has a more meanings. Local mean local. So the local maximum local mean can occur inside of an interval. Relative maximum are like the top of the hill, okay, top of the hill, and relative minimum are like the bottom of a valley. And you can see that they have as many local max and many local mean. So that means there's a many hill and many valleys. So it's up and down. There can be infinite many relative max or local max and local mean on an interval. But there is only one absolute max or absolute mean. Okay, only one absolute max and absolute mean. So you look at the function sine, cosine, you see that there is so many, they have an infinite number of the hill because the sine cosine is only less than 1 and greater or equal -1. So between 1 and -1. And there's so many hill and so many valley. Okay, so that's give you an idea of a function sine cosine has an infinite number of local mean and local max. Local extrema can be equal to the absolute extrema. Okay, for example, you can see that the quadratic will open down, which is a equal negative, like a negative x squared plus 5x minus 3. You see that there is a local max, and that local max is also an absolute max. And there's no local mean, no absolute mean in here. So everything going down to infinity, negative infinity, and infinity is no mean nor max. Okay. Now, on the other hand, if you look at the quadratic open up, then you're having a local mean, and that's also absolute mean, and there is no local max nor absolute max. So let's go into define the critical number. All right. The critical number is defined when f prime of c equals 0, or f prime of c is not differentiable, which is a DNE. Then c is a critical number. You can see that f prime of x on the left side is DNE. So actually it's f prime of 1 equal DNE. And you have f prime of 2 equals 0 on the right figure. Therefore, 1 and 2 are critical number of the function from the left and the function from the right. So local extrema can only occur at critical number. So if f has a relative or local mean or max at x equals c, then c is a critical number of f. That means f prime of c equals 0 or DNE. However, note, not all critical number have extrema. So not all critical number having a minimum or maximum. And I will give you example so you can see that not all critical number have extrema. If the function has extrema, then at extrema the derivative must equal 0 or DNA. But there is other critical number that is doesn't having occur at local mean or local max. So for example, you're going to see that the function x cubed that I draw here, and you see x equals 0, I mean x cubed, if you take the derivative, is a 3x squared. So therefore f prime of 0 equals 0. Okay, and that's a critical point. X equals 0 is a critical point, but it is not minimum nor maximum. Okay, and later we find out that the second derivative at 0 also equals 0, and using the second derivative, which we will learn later on, uh, it will tell us that point is not a local mean, local max, but it is an inflection point. So now we're gonna to apply by doing some example. Okay, and we have the three example here. We're gonna do that. So let's the first question asking you to find the absolute mean and absolute max of the function 3x to the 4 minus 4x cubed on the closed interval -1 and 2. So the first step we're going to do is we're going to take derivative. So now you know it's important to know to take derivative correctly. Otherwise, you're going to have a problem. This is the first step. And then make equal 0. And again, you have to know how to factoring that one, because solving the polynomial, you must know how to factor. And that's where AP exam, the own way having the equation that you must factor to solve it. Okay, mostly the non-calculator section. So here I factor 12x squared and make it equal 0. All right, I have to make it equal 0 to find the critical point, because here I don't rational, so I don't have denominator. So therefore I don't have the rational, so therefore I don't have in the uh, uh, vertical asymptote. So not worry about that part. So therefore there is no DNE involved here. So I sum that one, factor that equals 0. So therefore 12x squared equals 0, gives you x equals 0, and x minus 1 equals 0, gives you x equal 1. Now I got the point. Okay, we don't know that's going to be local mean, local max, but that's a critical point. So one thing we're going to do right now is looking at the value f of 0, f of 1. So f of 0 equals 0, f of 1 equal 3 minus 4. So that's going to be f of 1 is a -1. And also I have to looking into the endpoint, -1 and 2. So look at f of -1, and f of -1 will give us 7. And f of 2 will give us 16. Okay, so absolute max is here is 16 and occur at x equal 2, which is the right endpoint. And the absolute mean occur at the critical point, which is x equal 1. So absolute mean is 1 comma negative 1. And the one thing that you notice in here, x equals 0. X equals 0 is not a minimum or not maximum. You look at the graph, it's not a maximum nor minimum. And the reason being because you say that critical point doesn't mean that it's going to be local mean, local max. Okay. However, local mean, local max must be a critical point. And you can see that point here later on, we find out that's going to be second derivative equals 0, so therefore going to be inflection point. So that's going to be in probably in next few lessons down. All right, let's doing the look at example 2. Take derivative f prime of x, and that's going to give you 2 minus 2x to the negative 1/3. That's going to be 2 minus 2 over q root of x. So now, because we have a rational, so therefore x equals 0 is the DNE. So therefore, we got the critical number at x equals 0. And then the other one, we're going to solving the equation 2 minus 2 over q root of x equals 0. So we got two critical points. We're having the first critical point going to be x equals 0. And we're solving for 2 equal 2 over q root of x, and we find out x equal 1. Okay, the x had to be 1 because q root of negative 1 is negative 1, not 1. So therefore, there's only one solution here, which is x equal 1. Now we're going to plug into find out f for the two critical points and also add the two endpoints. So f of negative 1 equal negative 5. We plug in into the equation f of x equal 2x minus 3 to x to the 2/3. And we take f of 0, and f of 0 give us 0. And f of 1 give us negative 1. And f of 3 will give you around negative 0.240. Okay. So therefore, the absolute mean is going to be negative 1, negative 5, because that's the lowest. Negative 5 is lowest. And the absolute max going to be 0. Okay. That's the only one that is not negative. So that's going to give you 0, 0 is a max. Now, remember, 0 could be max as well if every other level is negative. So therefore, make sure that don't say, oh, 0 cannot be max. Yes, it can. Right? Right. So let's go into the last example. All right. So f prime is going to be equal to cosine. Remember that the outside is the power. So we're using a power rule. So going to be 2 cosines of x, and the inside is a cosine. So chain is give you negative sign, and sine gives you cosine. All right, and then you have to solve for equal 0. All right, so we have to factor cosines of x. So cosines of x, and then 2 negative 2 sines of x plus 1 equals 0. So the first factor cosines of x equals 0, which will give me x equal pi over 2 or 3 pi over 2. Remember that the closed interval is 0 to 2 pi. Negative 2 sine plus 1 equals 0. We solve it. We got sines of x equal 1 over 2. And that gives us x equal pi over 6, 5 pi over 6. So now we have to looking into those four critical number. Find f of pi over 2, pi 3 pi over 2, pi over 5, f pi over 6, f 5 over 6. But we have to looking into the endpoint as well. So f of 0 equal 1, f of pi over 6 equal 1.25, f of pi over 2, that's going to give you 1, and f of 5 pi over 6 equal 1.25. F of 3 pi over 2 is going to be equal -1, and f of 2 pi equal 1. So I look at the value of f in here, we see that the maximum, the absolute max occur at 1.25, and there's a 2x in there, two critical points. So pi over 6, 1.25, that is a 1 absolute max, and 5 pi over 6, comma 1.25, that's also the absolute max. Absolute mean is -1, only 1 point, one critical point, 3 pi over 2. That's absolute mean. Okay, so that's the end of the note. So I hope that, and don't forget to do homework.